Good day, grade 11s, and welcome to another video on acids and bases, which should actually be probably the final video before we move on to the next topic, which is in fact energy and chemical change. But anyway, so in this video, we're going to be looking at a couple of things just to close off acids and bases, and I have a past paper that I would like us to look at, just so we can practice and just bring in, or rather, just to test our understanding and the knowledge we've acquired so far, and just apply the knowledge we've acquired into a question paper just to see how much we understand and how far we are with content comprehension. Yeah. So today I want us to look at titrations. Yeah. So just want us to look at what we call titrations. Okay. So what exactly do we mean when we speak about a titration? What exactly is a titration? So a titration is a certain experiment that scientists will do in a lab. It's not actually just scientists. If you have time and you have the material, you could also just do your own titration at home. Obviously under the supervision of adults. But anyway, so titration is a certain experiment, right? That is conducted. It's like a certain type of experiment or method conducted in order to determine a certain concentration. Now, I want you guys to know, when I make use of these brackets, these just basically mean concentration. So just don't get alarmed when I use this. These are not just any brackets, right? So when we titrate, we talk about a titration as a method, right, that is used to determine the concentration of an acid, right? It's used to determine the concentration of an acid or the concentration of a base, right? So that's what we talk about when we talk about a titration. So a certain type of practical method that is used to determine the concentration of an acid or a base, right? And when we talk about the titration, or rather the concentration of an acid or a base, we then talk about what we call a standard solution. Talk about what we call a standard solution. Now, a standard solution, by definition, is a solution with a known concentration, right? So it is a solution with a known concentration. Known concentration. Okay. So it is a solution with a known concentration. That is what a standard solution is, right? And what you need to know is that if I titrate something, right? If I have a certain type of reaction, a titration reaction, a titration, it's not necessarily to say a titration reaction, right? So if I take if what I actually do in a titration is that we determine the concentration of an acid or a base, right? And we would actually try to determine the concentration of what we call the analyte, right? The analyte. So the analyte is basically some substance with an unknown concentration, right? It's a certain substance, some substance with an unknown concentration, substance with an unknown concentration, right? So what we do is that we try to determine the concentration of the analyte, right? And then we actually determine, or rather we determine the concentration of the analyte by using a titrant. So what is a titrant? What exactly is a titrant? A titrant is a substance that we actually add to the analyte in order to eventually get to the concentration of the analyte. So it's a substance that is added to react with the analyte. So we add it to react with the analyte. So we add it to react with the analyte. And you should know that oh my God. You should know that a titrant actually has a known concentration? A known concentration. Now, I'm sure there's probably a few of you that just wonder. I mean, if you say that a titrant has a known concentration and we say that a standard solution is a solution with a known concentration, doesn't that mean that a titrant is a standard solution? No, 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 it does not at all. Remember, when you talk about a solution, we are talking about bringing two things together to form a certain solution. For example, we talk about, think about it, if you have a salt water. Salt water is a solution consisting of two things, a solute and a solvent. What in that particular case is our solute? Sodium chloride. What is our solvent? Water. Water and sodium chloride give us salt water. That is our solution. And titrant, a titrant is a certain substance. A titrant can be used as a solvent or a solute. So it is not a solution. All you need to know is that a standard solution is a solution with a known concentration, and analyte is the substance with the unknown concentration, right? And then the titrant is a substance that we are adding so that it can react with the analyte so that we can determine the concentration of the analyte. And we'd say that a titrant obviously needs to have a known concentration, because if I don't know the concentration of a titrant as well as the concentration of the analyte and I react the two, there's really nothing that I'm doing. I'm just not gonna get anything out of that. Okay, so that is what an analyte is. That is what a titrant is, right? So how titration actually works? Just a brief talk. So a titration is, this is how it works. So in a titration, you just imagine it this way: there would be a certain volume of the analyte. So this guy would have a certain volume, right? Remember, he does not have a concentration, he does have a volume. So you would have a certain volume of the analyte in certain flask. So I just like to have my diagrams here. So just have a certain flask. Let's just have a flask right here. And in that flask, you would have a certain volume of the analyte. So in that flask, you would have the analyte, right? With a certain volume, with a known volume, right? And you measure that, and that volume's that analyte's volume within that particular flask. What you then do is that you start adding. You can burette, you can use a burette, or you can use a pipette. You start actually adding your titrant. So in this particular burette, you have your titrant. What you actually start doing is you slowly add, drop by drop, you slowly add your titrant within this particular analyte. So remember, in this solution, we have our analyte, and it's a different color. Sorry. Oh, okay. Let me just use this. Okay, no. Oof. Okay, so I have my analyte in there, and then I start pipetting my drops of my titrant, right? So a titrant, this guy in here will be my titrant. And my titrant has, remember, a concentration. Why would I say that? But it has a concentration, and it also has its own volume. But this guy, the analyte, does not have a concentration, but he has a volume. Cool. So I then start pipetting small drops of the titrant within the analyte and then just mixing them together, right? So we then use an indicator, could be any indicator, just so we can, the use of the indicator would be to determine whether or not the what we call the endpoint has been reached. But these are not really some things that you really need to know for the exam. It's not exam relevant. But as I titrate, what happens is that I reach the endpoint. Now, what exactly is the endpoint? Now, the endpoint is basically when I talk about an endpoint, I'm basically saying that there is a certain concentration of the titrant added to the analyte, right? So what happens? So at the end point, what do you expect to see? We are expecting to see that with the reaction of the titrant and the analyte, we have reached a completion. So we have the reaction between the titrant and the analyte is complete. That is the end point. And at that particular moment, what is observed? We then observe that the amount of the titrant added, right? The amount of the titrant added is exactly equal to the amount of the analyte present. So when we talk about the titration, so I have a certain titrant in my, so I have my analyte, could be any substance, right? Just don't think too deep about the terms used. So my analyte could be any substance that I would titrate with the titrant, right? And remember, the titrant has a known concentration and a known volume, and the analyte has a known volume but not a concentration. Then at the end, as we keep titrating, adding drop by drop by drop of the titrant, we reach the end point. The end point is the point where you realize that, okay, so now I have an equal amount of my titrant as well as the equal amount of the analyte, right? Okay. So that is how a typical titration experiment works. Now remember that we had said that in a titration, we are trying to determine the concentration of the acid or the base, right? So in a certain titration, we wouldn't really know which one exactly is the titrate, is the acid or the base, right? Well, you would know that your analyte could be some particular acid and your titrant could be some particular base. But with the reason you would titrate something is so that you could eventually get the concentration of the analyte, because it is the substance without a concentration, right? So after the endpoint has been reached, we then measure the volume of the titrant that was added to the analyte in order to reach the endpoint, right? What then happens? We then determine the concentration of this analyte, right? Using the volume and the concentration of the titrant. Now, that is when we talk about the stoichiometric ratios. Those stoichiometric ratios. Okay. So I would use this guy and this guy to get my number of moles, and then I would use the stoichiometric ratios to determine the number of moles of the analyte, and now I would have the number of moles of the analyte as well as the volume, and then I can determine my concentration. Okay, cool. So a typical example, I feel like using the words titrant and just becomes a bit confusing. Let's say we determine, we are trying to determine now, I mean, this one should be fairly easy, right? So if I try to determine, say for example, I am trying to determine the concentration of hydrochloric acid, right? So I want to determine the concentration of hydrochloric acid, right? So what do? I then use sodium hydroxide to determine the concentration of hydrogen chloride or hydrochloric acid. You then identify the hydrochloric acid as your analyte. Why? Because you are trying to determine the concentration of hydrochloric acid. You do not have the concentration of hydrochloric acid. Remember, when we say an analyte, we say it's a substance with an unknown concentration. In this case, hydrochloric acid was then our analyte. And then obviously, the sodium hydroxide would then be our titrant. Okay. So you would have a typical reaction of sodium hydroxide with hydrochloric acid, and you would get something like this. So it's first to second, second to first, okay. So that gives us sodium chloride plus water. Okay, now remember, we've identified this guy as our titrant and this guy as our analyte. So notice something. We titrate the analyte using the titrant, right? So we have a titrant and an analyte, and we keep slowly adding, we keep slowly adding the titrant to the analyte so that we can reach the equivalence point. And at the equivalence point, What do we know? When we reach the equivalence point, we measure the volume of sodium hydroxide added. We measure the volume of the titrant added. What volume of the titrant was added to the analyte in order to reach the endpoint, right? Remember, the endpoint is a point where the amount of sodium hydroxide added is equal to the amount of hydrochloric acid that is in the particular flask, right? And then from there, what then do? We then say, okay, once I have determined the number of, once I have measured the volume of sodium hydroxide that I've added, and I would obviously know the concentration, right? And I can get the number of moles. Remember, C equals to N over V, such that N equals to the product of C and V. Once I have that, I can then determine the number of moles. So these are the number of moles of sodium hydroxide at the endpoint, right? And now I can get the number of moles of HCl using the stoichiometric ratio, right? Once I have determined the number of moles of HCl, I can then say, so the number of moles of HCl would be equal to the number of moles of sodium hydroxide. Why? Because they have a ratio, they have a certain ratio of 1:1. So a 1:1 ratio tells me that the number of moles are equal. Once I have the number of moles of this guy, I can then use the equation C equals to N over V and then get the concentration. Now you notice, I would then at the end determine the concentration of HCl. Okay, I think I've said a lot. I've said quite a lot. Some of the things I've said might be a bit hard to decipher, but just if you could think about it, it's just, you don't need to worry much about how the titration occurs in a certain lab experiment. Just know what the observations that you make and how you eventually get to calculating the concentration of either the acid or a certain base that you use. Okay, cool. Now that is when I bring you to this particular equation. Talk about the equation that says CaVa over CbVb equals to Na. Might want to make this a little bit bigger. Na over N, okay, it's a bit small, over Nb. Okay. So, as you know, for every equation that we write, we need to know what each variable represents, or each letter represents, right? So you should know that Ca represents, obviously, hold on, just not say C, because I want to say something really important. So C represents the concentration. So C is the concentration, right? And you know that V would be the volume, right? And N would be, now most of you are thinking N could be the number of moles of a substance. I wouldn't say you're wrong, but in this particular case, I would like us to think of N as the molar ratio, the molar or the stoichiometric ratio. Stoichiometric ratio. I'm going to show you why. So now the reason I did not write VA, CA, VB, CB is because, so I'm just going to remove this guy here so I can have more space to write. I want you to look at something. So let's take a typical example that we had. So we had NaOH and we had HCl, and that gave us salt plus water. Right? So if you had to use this equation, one would actually say, okay, so if I had to bring this equation and use it, what would I actually do? Okay, just, oh, Jesus Christ. Okay. Okay, just bring this side. Okay. Right, so if I had to use this equation, what would I do here in this particular case, in this example? It really does not matter whether you choose your A as sodium hydroxide or hydrochloric acid. What am I saying? I'm saying that I can choose sodium hydroxide to be my base. In fact, it is. I wouldn't necessarily say I can choose. And then HCl be my acid. Similarly, I can say my sodium hydroxide will then be my acid and my hydrochloric acid be my base. I am not saying that is true. I am not saying that sodium hydroxide is an acid, and I'm not saying that hydrochloric acid is a base. Please do not get me wrong on that part. That is not what I am saying. Now, the importance of saying this is this. If I chose to use this equation, I would be given a certain number of moles of sodium hydroxide, right? Say we are given a certain number of moles of sodium hydroxide. So the number of moles of sodium hydroxide given, sorry, not the number of moles, but the concentration. So the concentration given would be 0.1 moles per cubic decimeter, right? And let's say we are given a volume of sodium hydroxide as 25 25 milliliters, right? And so it's 25 milliliters. And then I realize that, and then I'm given my concentration of my HCl. Oh, sorry, remember we don't have this guy. So the concentration of HCl, we wouldn't really have. And then we have the volume of HCl, which would be, say, 15 milliliters. Okay, so, and then I decide to use the equation CA over CB VB, which is equal to NA over NB. Okay, let's just grab my calculator on this one. Cool. Now, notice something. If I choose to say that my CB VB would be the concentration of a base, right, with my volume of a base, then I say sodium hydroxide is my base. That means I would have in the denominator the concentration of my base being sodium hydroxide is 0.1, and the volume of my base being sodium hydroxide would be 25 milliliters. But notice something. This is in milliliters. We know that we want it in cubic decimeters. I want you to note something. 1 liter is equivalent to a single cubic decimeter. Sorry, just not negative. Right. So 1 liter is 1 cubic decimeter. But 1 milliliter, sorry, 1 liter is equivalent to 1,000 milliliters. Meaning if I had to get from a liter to a milliliter, I need to multiply by 1,000. And to move from that guy to that guy, I need to divide by 1,000. Right? So if I want to move from 25 milliliters to liters, I then divide 25 by 1,000. Right? So I'm going to have it here, 25 over 1,000. And then so what would I have at the top? So you would obviously have to choose your acid as your hydrochloric acid, but you don't have Ca, yet you have Vb as 15 over 1,000, right? So what then would be your Na? Now remember, they are at a 1:1 ratio, and I did say that your Na and Nb should be a stoichiometric ratio, so you're expecting them to actually be at a ratio of 1:1. So this is the ratio of the base. This is a stoichiometric coefficient of the acid. Sorry, this is yeah, I feel like I used two different words that actually mean the same thing, but could be quite confusing. So 1 is the stoichiometric coefficient of HCl, and 1 is also the stoichiometric coefficient of sodium hydroxide. So in this particular case, I would have Ca times 15 over 100, over 1,000. Remember, I just cross multiplied. And that would also be, what is 0.5 times? So it's 0.1 times, sorry, just 0.1 times 25 divided by 1,000. And that gives us 0.02. 0.025. Okay. So if I divide that and I solve for A, I would get my A as 15 divided by 1,000. I would get my A as 0.167 moles per cubic decimeters, right? So I'll get my Ca as 0.1 moles per cubic decimeter, 167 moles per cubic decimeters. But here's what I wanted to actually show you. Let's say, so this is the answer that we collected, right? So our Ca, this is our final answer. So I'm just going to take that and I'm going to put it here. Right, so let's just say I chose to make my Ca sodium hydroxide. Okay, let's see what I was actually talking about. So I have Nb, right? I would then say, if my Ca is sodium hydroxide, then this is what I would have. I would have Ca, which is a concentration of sodium hydroxide, as 0.1 times Va, which is the volume of sodium hydroxide, as 25 over 100, sorry, over 1,000. And then I would have here concentration of B not have, and then Vb would then be 15 over 1,000. And then obviously this would still be 1 over 1. And then I would still get 0.0025 equals to Cb times 15 over 1,000, right? And then I would still get my Cb as 0.167 moles per cubic decimeters. So you notice something. It really doesn't matter how, and obviously you would actually have to conclude at the end that therefore the concentration of HCl is this guy over there. So what you could realize here is that it really doesn't matter which one you choose as your Ca or your Cb, if you know that if you change the order in which it should be, then you also need to change the stoichiometric coefficient. So say, for example, just a hypothetical thing, that okay, so let's just say that these two were at a 2:1 ratio. They never at a 2:1 ratio. If you have sodium hydroxide and HCl, you can never get that. But let's just say it had. So let's say for every sodium hydroxide is to HCl, you had a ratio of 2:1, right? So if you have a ratio of 2:1, I think I shouldn't use the word. I shouldn't have used the word never when I made an example. Okay, but so if I had to have a ratio of 2:1, that means these guys will change, right? So I'm going to have to change these guys to what? If I have chosen Ca and Va as my sodium hydroxide, then my Na must also go according to the Na of sodium hydroxide, meaning I'm going to have to have a 2 here and a 1 there. But if I have to choose the other way around, where my Ca and my C and Va was hydrochloric acid, that means at the top I would have to have my 1, and at the bottom I would have my 2. Okay, I really hope I'm making sense. Okay, so that's why I actually just said it really doesn't matter. And another thing, when it comes to the concentration, the volume, if I know that the volume of HCl is 15 milliliters, and the volume of NaOH is 25 milliliters, it really doesn't matter if I substitute these volumes in the equation without actually converting it to cubic decimeters. Why? Because at the end of the day, for as long as these two have the same unit, SI unit, it really doesn't matter whether you change it or not. But if you decide to change it, you need to make sure that you convert both of them. If you convert, but if you don't convert, then you need to maintain both of them in milliliters. If you convert, you need to convert both of them into cubic decimeters, right? Though that's just another important thing that you guys need to know. But I suggest that just continue converting the way you should actually convert, the way you actually know how to convert, and knowing that your volume should be in cubic decimeters for as long as you're doing chemistry in grade 11 as well as in grade 12. Okay, So we have looked at the equation of a titration. We have also looked at another thing, just a fun thing. Just gonna add these conversions here. It's very important for you to know, like I said, that 1 liter, a single liter, is equivalent to a single cubic decimeter. A single liter is equivalent to 1,000 milliliters. So milliliters ml. And you can also then say, since this is true, you can then say 1 cubic decimeter is equivalent to 1,000 milliliters. What else? You also need to know that 1 milliliter is equivalent to 1 cubic centimeter. That already tells you that from this guy, sorry. Since 1 milliliter is equivalent to 1 cubic centimeter, that means that 1 cubic decimeter is equivalent to 1,000 cubic centimeters. Okay. Right, so these are just the conversions that I want you guys to have. Okay. So what I want us to look at next is what we call the hydrolysis of salts. The hydrolysis of salt. Okay. So what do we talk about when we talk about the hydrolysis of salt? We are talking about a reaction of a salt with water. So it's the reaction of a salt with water, right? So that's what we talk about when you talk about the hydrolysis of a salt. All right, but what exactly is a salt? I mean, you're not wrong, NaCl is a salt, but why do we say that? Well, for starters, because when we buy the package, it actually says table salt. So that's why sodium chloride is a salt. But anyway, okay. So we say that we are talking about the hydrolysis of a salt, and we're talking about the reaction of a salt with water. So let's look at this. So by definition, a salt, right? So by definition of a salt, what exactly is a salt? So what exactly is a salt? A salt is a certain substance, right? It is a certain substance in which the hydrogen, right? In which the hydrogen of an acid, sorry, in which the hydrogen of an acid is replaced by a certain metal. So those metals could be your group 1 metals or group 2 or other metals in the periodic table, right? Remember, group 1 metals, we call them alkali metals. In group 2, we call them alkaline earth metals. Okay. Well, I'm not strictly saying it's just group 1 and group 2. I mean, if you have silver, remember silver is not in group 1. It is actually in between the table. It's just next to, so it just lies between copper, palladium, cadmium, and aurum. Just find those 3, and in between those 4, in between them, that lies silver. Okay, so an example of a salt would be, well, for starters, we spoke about sodium chloride. Now notice something. How did sodium chloride get to be a salt? Well, we had our reaction of NaOH plus HCl, and we resulted in NaCl. Remember from the previous videos, we had first with last, second with first. But in this particular case, I just want to show you something. So you just have sodium hydroxide, and you notice something. In HCl, you had a hydrogen. In NaCl, you have a sodium metal. So in HCl, you had a hydrogen. and it was replaced by a sodium metal to give you the salt sodium chloride, right? So you have your HCl with your hydrogen. Remember, by definition, you're replacing the hydrogen of an acid with a metal. So you're replacing the hydrogen of HCl with a metal, Na. Therefore, you result in NaCl, which is our salt, right? By definition. And how I would actually like to remember it, how I would remember it, and how I also we prefer my kids remember it is this way. So if you have something like this, so it's like in salt, you would typically have some metal and some non-metal, right? Okay, that's a salt. Yes. So I would say it's some metal and some non-metal. Say, for example, sodium chloride once more. So sodium chloride, what do we have? We have some metal and we have some non-metal. Again, we look at magnesium hydroxide, magnesium chloride, magnesium chloride. What do we have? We have some metal and some non-metal, still a salt. What do we have? We have potassium chloride. So if you have potassium chloride, what do we have? We have some metal and some non-metal, right? What else do we have? What else do we have? We could have calcium fluoride, calcium fluoride. Now you notice with calcium fluoride, we have some metal and some non-metal. That's just how I used to remember it. But if you could remember it using the definition, that is also correct. That is definitely correct, actually. It's just my way might be a bit confusing. So just please follow the way of the definition. Okay, so that is what we define a salt as, right? So what you need to know is that during the hydrolysis of an acid, right? So during the hydrolysis, remember the hydrolysis is the reaction of a salt with water. So during the hydrolysis, right, what happens? We are more likely, sorry, not more likely, but we really need, we are basically forming a salt, right, that is either one of the three things, that is exactly one of the three. Can either be an acid, or can either be acidic, basic, or neutral. So that's what we talk about when we talk about how a salt formed should be. So I have an acid with a base. I have my salt. So my salt can either be one of the three things here. It can be acidic, it can be basic, or it can be neutral, right? And we know that when we say something is neutral, we say that is obviously it's just that 7, it's neither acidic nor basic, right? It's just neutral. Okay, so your salt can either be any of those things during hydrolysis, your resulting salt, right? Now, that comes with the condition. The condition is that the acidity of a salt is dependent on the relative strengths of the acid and the base that is used, right? So it is dependent on the relative strengths of the acid and the base that is used. That is when I bring you to this particular thing. So you would have something like this. What you need to know. So this is a certain form that you need to follow and never forget. If I react a strong acid, for starters, if I react a strong acid with a weak base, what am I expecting to get? I am expecting to get a strong, sorry, not strong, but I'm expecting to get a salt that is acidic. Why? Because I have the reaction of a strong acid with a weak base. I mean, it's basically obvious. I mean, think of it as a fight. So if you fight with someone who is way bigger than you and way stronger than you, um, you're more likely to just win the battle. I mean, lose the battle, right? But it's not. I mean, think about it. So you are fighting with someone bigger than you, older than you, stronger than you, right? So you are at a battle with that person, fist fight. Just punches and blows going around everywhere. So you are fighting that big guy. So if you are in this case the weak base, and the big guy is the strong acid, right? So what happens? Obviously, just a few punches to the face, you drop down. The big guy wins. So the guy who's strong takes preference, right? I mean, he becomes more dominant, rather. I think that's better terminology. So the guy who's strong becomes more dominant in the resulting salt. So I have a strong acid, right? So my strong acid with my weak base, my salt will then, my acid will be more dominant. That is why your salt will be acidic. You have a strong acid with a weak base, your salt will be acidic. Why? Because the acid is stronger than the base, meaning the acid wins the fight. So the strong acid with the weak base has the acid winning the fight because it's stronger than the base. So when the acid is stronger than the base, it wins the fight, therefore your salt becomes acidic, right? Similarly, if you had a weak acid, with a strong base, a weak acid with a strong base, what would you have? You would then have a salt that is basic, right? Or that is a base. Why? Because you are reacting something weak with something strong. The strong guy becomes dominant in the salt. That's why you have a basic salt, because the base was strong. The base was stronger than the acid. That's why you result in a salt that is basic, right? Cool. So if you result in a salt that is basic, that is what you typically would have. Okay. So a weak acid and a strong base give us a salt that is basic. And then in this one, we have a strong acid. We have a strong acid plus a strong base. What are you expecting what are you expecting your salt to be? Ah, neutral. Because you have a strong guy with a strong guy, they beat each other up, they both take each other down. So I give you a punch, you give me a punch, we both drop down. We are both unable to get up, meaning none of them are dominant because both of them lost. So your salt would then be neutral. It would have it would have no acid, it would be neither acidic nor basic. You would say then it is neutral. That is when you have a strong acid with a strong base. Okay, so this is basically the form that you would actually have to never forget. Right? Just never forget that. Okay, so what have we looked at? We have looked at titrations, right? And we have looked at the equation associated with the titration. We have explained what a titration is. We have looked at how titration works. We have also looked at the hydrolysis of salts and this particular form in which a strong acid with a weak base is a salt that's acidic, and so on and so on. And we've defined exactly what a salt is, and we've defined what hydrolysis actually is, right? So another thing that I'd just like to throw at you is this. We need to remember that an acid ionizes. I've always had a problem with spelling because it's like some people have it this way and some people have it with a Z, with an S. I just never know which one is correct, but I'm just going to stick to this one. And we say that bases dissociate. Dissociate, right? I want you to guys know something very, very important. We need to talk about the relative strengths of acids and bases, right? What do I mean when I talk about relative strength? I am talking about the fact that the relative strength of an acid or a base would depend on the ability of that particular substance being able to ionize or dissociate. Remember, keeping in mind that acids ionize and bases dissociate. Okay, you need to know that in water, a strong acid ionizes completely. So a strong acid ionizes completely, right? I think I'm just gonna have the in water part is like a certain, like a just a heading, just So in water, in H2O, the following applies. A strong acid ionizes completely, and a weak acid ionizes partially or incompletely, but just stick to partially, right? So a strong acid ionizes completely and a weak acid ionizes partially. So what do I mean? I mean that if I had to take a strong acid like HCl, when HCl ionizes, we're expecting HCl when in water, HCl, when you add it in water, this is what happens. You result in a hydronium ion as well as a chlorine ion, a chloride ion. So, notice something. HCl was put in water, right? It ionized completely, right? Because HCl is a strong acid, so it ionizes completely. When I say it ionizes completely, I mean it basically just disintegrates into its respective ions, right? Without forming any type of HCl within that particular solution. So when you put HCl in water, it just disintegrates fully into its respective ions and not its ions as well as HCl itself, right? So that's what I mean when I say that it ionizes completely. If you look at something like a weak base, right? A weak base like, a weak acid. Take a weak acid like carbonic acid, right? And with carbonic acid, I would have something like this. I would have it in water, and then I would result in this. I would have my hydronium ion with my carbonate ion, right? But also, if I might remember, there's two of that, so I should have two hydronium ions. But in my solution, I will not only have those particular ions, but I would also have H2, oof, bad writing. But I would also have H2CO3. Now, why is that? Notice something. So when ionized, it became its respective ions, right? But it also had itself in the solution. That basically means that when it ionized, it did not ionize fully. When I mean ionize fully, I mean this whole thing disintegrates into its respective ions. But in this particular case, it ionized partially because this whole thing did disintegrate into its respective ions, but it also just went in the solution as itself. So that just means that it did not ionize completely. To ionize is to form its respective ions, right? So it did not just form its ions, it formed its ions as well as itself, meaning it ionized partially. But you notice with HCl, this whole thing formed its ions H3O plus as well as Cl minus without HCl actually having itself in the solution once again. So that is why we say that a strong acid ionizes completely. What does that mean? It just forms its respective ions in solution. But when you have a weak acid which ionizes partially, that means that you have its respective ions in solution as well as itself, right? Because not the whole thing formed the hydronium and the carbonate ions, right? Okay, so the same applies when we talk about bases. So we look at a certain weak base. Sorry, just before I go on, very important. You guys need to know that, just gonna make this in red because it's very important. Just in NB, a strong acid forms a weak, oh, I just wrote a strong. So a strong acid forms, oh, okay, this is a lot going on here. I'm just gonna have it in short, you know, just for the safety of it. What do I look what you made me do? Okay, so a strong acid, for starters, a strong acid forms a weak conjugate base, right? Similarly, a weak acid forms a strong conjugate base. Okay, very, very important point, right? Okay. Anyway, moving on. Now we look at the bases. So a weak base. Remember what do bases do? Yes, dissociate. A weak base dissociates partially. And a strong base, what does a strong base do? Aha, a strong base ionizes completely. Okay, so a typical example of a weak base would be, think of it as this is magnesium hydroxide. So if I have magnesium hydroxide, it's a weak base, by the way, and I reacted, and it dissociates, right? So when magnesium hydroxide dissociates, this is what happens. So when it dissociates, it forms Mg 2 plus and 2 hydroxide ions. But remember, it's a weak base. What does that mean? Yes, it is then going to form magnesium hydroxide once again. Because when something dissociates completely, then we know that it needs to just form its respective ions. So if I have this guy, this entire guy must give me these two and these two. And that's when I can say it's a strong base. But if I eventually lead to that guy as well, I mean himself, that just means he's a weak base because he gave me his ions, yes, but he also gave me himself again in solution, meaning it did not dissociate completely, meaning it did not fully disintegrate into its ions. It partially disintegrated to its ions, and the other half part would be itself. That's why we say dissociate partially, right? And then with a strong base, I mean, a very common strong base is potassium hydroxide, right? So potassium hydroxide, what happens? So potassium hydroxide forms potassium plus hydroxide ion. This is not going to form. Why? Because potassium hydroxide is a strong base. So we remove this guy and we only result in these two. So we say it's a strong base because this entire guy formed his respective ions and not itself once again. Right? So you notice that it's almost similar to an ionization of, it's basically similar to how acids ionize and dissociate, right? But we have an exception, a very, very important exception. The exception is that Ammonia is the only base that ionizes. Remember that we say bases dissociate? Yes, it's different with ammonia. This guy is so special that he is the only guy that is the only base that is allowed to ionize. Meaning, if I have to have a reaction of ammonia in water, right, what would I have? I would then result in a hydroxide ion as well as an ammonium ion, right? So notice how this guy in water gave me his ions, right? But he did not dissociate. He actually ionized. Wow, special guy ammonia really is, hey? Okay, so that's what we look at when you talk about strong acids and weak acids, strong versus weak acids and bases, right? Just very, very important things. And just another thing also for bases, you need to know and be that a strong base, what do you think a strong base does with its conjugate acid? Aha, a strong base gives us a weak conjugate acid. Similarly, a weak base gives us a strong conjugate acid. Okay, very, very important things. Now, what have we looked at? We have looked at titrations, we have looked at hydrolysis, we have looked at how strong acids and weak acids ionize and how they fully ionize or completely or partially ionize. We've also looked at how bases dissociate fully and how strong bases dissociate fully and how weak bases dissociate partially, and the exception of ammonia, right? Okay, now that brings me to the end of this video. So in the next video, we're going to be looking at a few past exam question papers, just so we can look at how we can maneuver around acids and bases, and just so we can go into that exam hall and just mouth that distinction. Okay, but from me to you, I shall see you guys in the next video. Thank you very much. Have a great day.